So good afternoon, everyone. Actually, the title is a little different. We're going to be talking about the interparticle spacing model to maximize filler content. So I work at the Oak Ridge National Lab. This is a project that is being sponsored by the DOE through 2 offices and involves 2 academic partners and 6 different industry partners and the 2 national labs. So very quickly here, we're talking about decarbonization, right? We know that there are 2 main pathways to achieve decarbonization in the short term. Those are increase the efficiency of cement and expand the use of supplementary cementitious materials, okay? So in this project, what we are doing is trying to increase the efficiency of cement by extracting more megapascals than what's done currently, which means we replace cement by other things, we still keep about the same performance. So we use particle packing models and mobility models, and we develop what we call the high filler, low water, or HF LW concrete. And this technology has been described by Professor Vanderlei John and his group in 2018, a publication from CCR. The thing is, when we increase the packing density of the system, you expect that the rheology is going to be affected. So throughout the whole project, we need to keep an eye on rheology, make sure it's working well. So here I'm describing this effort to implement this technology in the US precast prestressed concrete industry. So I don't know if you have seen this model before. It was a spectrogram, is a description of what the model. Do I have a... Oh, it's so tiny. Okay. So if you imagine that being your concrete slice, right, the large yellow particles are the aggregates and the blue is the paste. If you can zoom in, you will see cement agglomerated and the pockets of water and air. Then you use superplasticizers to disperse them. The current ratios of superplasticizers that are used by the industry today allow some dispersion, but not a full dispersion, so you still see those pockets there. If you are able to fully disperse the particles using the dispersants, you would be able then to maximize the packing by adding small particles in between the cement grains. And also in this technology, we not only do that, we also replace part of the cement by filler as well. So here we are working with limestone fillers, okay? And I wanted to show you this technology has been actually compared to current traditional concrete. This graph correlates the binder intensity, which is the mass of binder that includes cement, fly ash, slag, pozzolanic materials, per cubic meter of concrete to deliver a megapascal at 28 days. Okay, so that's the BI, is the efficiency of the cement. So all this big cloud here is the data from the literature from 156 articles worldwide that plot this binder efficiency against the strength. So you can see, you know, there's this red line kind of limits where the technology, the traditional technology is. The colorful markers are high filler, low water mixes practiced by groups outside the US. Okay, so there's no work, I mean, the Oak Ridge National Lab now is leading this work in the US. Before that, there was not, I think, to my knowledge, that people working here in the US. Anyway, you can see that a number of mixes fall under where the current technology is. Which means if we can decrease the binary intensity, we can decrease the carbon footprint, right? So our partner that I'm describing here today, here where they are, the star, and we want to move them here, we're going to decrease by half their binary, or increase their binary intensity by, efficiency by half. So we use a couple of models, and they are very traditional. I mean, we could use, there's a number of different models that you can use for packing. We decided to use this one very traditional from 1930. So this article is available, you know, in the literature. You can go and read. But we do use this model. Here's the algorithm to obtain the apparent volume of the granular system. And this is for the entire system. Now, we're not only talking about the aggregates, we're talking about aggregates and fines, right? And we get here this apparent volume of the worst situation. And then we use another equation that was proposed by Funk and Zinger in '94, in which using the apparent volume of Westman and Hugel, you can now estimate the distance between the particles. Okay, so the IPS formula is here, is the interparticle separation, it's the distance between the fines, and the MPT is the maximum paste thickness, is the distance between the coarse, which is the aggregates, sand and coarse aggregate. You see the equation is the same. It depends on the volumetric surface area of the materials, depends on the concentration of solids in the mixture, and the porosity, okay? Or in the case of the fines, is the porosity between the cement and the fine grains. And in the case of the concrete, the POF becomes the paste volume. So now you have the paste between the particles of aggregates. So what we did here, so the experimental part, we are working with type 1L. All the precast producers are being pushed to use 1L. So that's what we use here. We have two fillers, one fine filler, calcitic nature, and one coarser is a dolomitic one. We have a natural quartz sand, crushed limestone as coarse aggregate, and polycarboxylate-based dispersants. And here is the properties of them. I mean, again, highlighting the difference in particle size distribution, the compositional nature of the fillers, and their surface area. Here we see filler 1 as the finer with the higher surface area. This is just to show the particle size distribution of the different materials. So you can see here is the fine limestone, cement is the blue, the coarse limestone is the other one here, sand and aggregate, okay? We don't want to fill these voids, okay? We want these gaps to be present, okay? That's a trick. On the experimental part, the first step is, remember, we want the system to be fully dispersed because then we can apply the models. The models do not work if the particles are not fully dispersed. So we determine how much dispersion we need for each individual material. And after that, we compose the paste in binary ternary paste as we wish. Okay? We use the techniques to determine how much dispersion is rheometry, bob and cup rheometry, using the high shear mixer by this standard. And we check what's happening to the cement chemistry or cement hydration kinetics as we do that. And once we test our paste, we then try to correlate the model, which is the IPS, the interparticle separation, to the rheological and kinetic parameters. And this is our regimen. Here's the shear rate and the time for the testing. We then move to concrete. And here we start with the reference concrete. So we know what they are using today. We go there, we start varying from where they are. We then estimate the MPT using our model, and we target to keep the yield constant, and also the similar paste volume they are using today. We don't want to change that too much unless we can improve from where they are. And we check that by measuring the MPT or by estimating the MPT. So this is the first set of results. This is where we determine how much dispersion we need for full dispersion. So here is just one of the rheological parameters that we chose for this. So we do a dose ramp of the dispersion, and when it plateaus at the bottom, that's what we need, full dispersion. So each material has an amount of dispersion that is needed. Cement calls for more because it's more reactive. And then when we compose the paste, we do an average, a weight average amount of the dispersion. In this case, depending on the composition of the paste, it range between 0.33 to 0.42 solids on solids. And then when we look at the calorimetry parameters, we see that the dispersion has a linear impact in extending the set time and reducing the heat evolved after 12 and 24 hours. Remember, this is precast. 12 hours cannot be badly affected. So here we become conservative. We choose a lower amount of dispersion, the 0.33, because we don't want to retard the system too much. Then we do our rheometry test, and then we come and we want to correlate our IPS to the apparent viscosity, which is really the signal out of the rheometer. And we get these empty markers here. No correlation, right? Actually crazy. As you increase the IPS, you want to see the viscosity going lower. And here you see it's going higher. So something is odd here. So we decided to go and try the model, rheology models, and we found a very good correlation of the Herschel-Buckley model. And the consistency index as the full marker here, you can see has a very good correlation with our IPS data. And then this plateauing of the consistency index means that bases are becoming more stable, okay, as you are testing them. The thing is, this is happening. We don't find this correlation with apparent viscosity because our testing is dynamic. We are increasing the shear rate, and then we are decreasing, and we're increasing again. So we're always moving in a different pace, and then the pace has no time to equilibrate. And that's demonstrated here. Once we fix the shear rate, we see the rheological parameters changing over time. Okay, so that's an evidence the paste are not in equilibrium. So we also found good correlation between also the packing parameters, in this case the specific area, with the kinetic, cement kinetic, hydration kinetic parameters. So here you can see higher surface area. We have a higher heat evolved after 12 and 24 hours, and we have a shorter set time. So they are all these factors correlated. So these correlations show that the IPS is a good indicator of high filler, low water paste rheological behavior and has the potential to help us designing this paste. There's a strong correlation between the parameters measured and estimated, but we also always need to consider this adequacy between rheology and impact on hydration kinetics, okay? So with the model, we can do infinite number of simulations. So this is for this one producer. That's their reference concrete right there. And things that we pay attention here, we look at the cost. Okay, so this highlighted line here shows the percent of cost. As we move to the right, those are all high filler, low water pastes. We can see that we are between around like plus minus 3% of the cost of their current mixes. We look at the IPS. Remember, the higher the IPS, the more this concrete will flow, the lower its viscosity. The higher the MPT, likewise, the concretes move faster or easier. One thing to break a paradigm here, water to cement ratio, we actually higher in all our mixes. And this is because we are pulling more cement than we are pulling water out, okay? But even with a higher water to cement ratio, we have a lower water to solids ratio, and that's what actually works very well on the performance. We are able to keep performance even with a substantially higher water to cement ratio. So we do the simulations, then we go to the lab, and then we want to see what happens. How can we mix those things, right? So here you see, so this is a concrete rheometer that does the mix and measure rheology as you are mixing. Right? So you can see the torque as you are mixing. It's also the good thing also is a pen mixer type. So you are able to, which is exactly similar to what the precasters are using. So this chart shows here the behavior of the torque on that rheometer and the time. We are not saying we're going to mix the concrete for 25 minutes. Just for your information, it mixes in 9 minutes in a dry mixer, in a drum mixer as well. Here we just wanted to see what happens. So first we add the powders, then we drip the water with the dispersant. So water comes after the powders and the sand. And here we can see the reference and the high filler, the orange one here, having about the same torque. And when we add the stone, this is when we see a big difference between the high filler and the reference. We now need more torque to move the high filler. However, this is our first series of tests. All the concrete high filler can be modified so we can match the energy that is needed for the reference. Okay, we can play with the granulometry, we can play with the chemical industry. Oops, sorry. So from our lab experiments, we were able to obtain a cut of 51% of cement, and by adding 50% of fine zone weight. We cut water by 23%. We increased the dose of dispersant by 3 times. We are adding accelerator, non-chloride, as recommended by manufacturer. Our water to cement cementitious ratios we already mentioned. In the lab, we obtain a 7% drop in cost. It spreads as an SCC. As you can see here, it's a beautiful concrete. Initial and final set times, we measure by ultrasonic pulse velocity, and is about the same. And the compressive strength is similar or higher with the high filler at 12 and 24 hours. So from there, we went to the plant. And so these are results from a lab trial at the plant, so not yet industrial. So the intent was to bring the concrete to them, let them mix in their lab with their mixers and see what they feel. So they did a number of different interactions. They're ready to go, very research-oriented, did a number of different high filler, low water mixes. Here are the reference. There's 2 mixes here, the reference from the mixer, the 5-yard mixer, and the reference made in the lab. And there's 3 different shades of color here, 3 shear cycles we do, waiting 5 minutes in between each. So we see there is some buildup of the properties here. The best mix that we had was this blue one here, which is not too different. They are the same scale. So sorry, this is torque, and this is time, okay? So the blue one was our best high filter, low water result. We still have room to improve, and we're going to work on that to come to the level of energy that requires the reference mix. So from that experimentation there, all the high filter, low water were SCC. 20 hours and 7-day compressive strength are within spec. We do need to further refine. We can cut more water and or dispersion. It was a little too fluid. And the cost is within 3% now. It became a little narrower. Okay. So here I want to see if I can show. I want to show how it flows. Okay, so I'm going to pull it out. I want to run this video. Oh, here it is. Okay. So you can see the contour.
Yeah.
Still gray, light gray. So there was a few interactions before we went, iterations before we got to that level. There's more chemical admixtures than we had initially put. But there you go. And the precast producer said he would put that.
Yeah, see, we don't have a crown here.
So in the end, so that was our initial in the lab, right, without the producer here. This is after this lab at the plant, so we kept the same. We actually had to adjust the water a little higher. They wanted to test a different chemical mixture, a little less efficient but not as air entrainer. So it was actually a better admixture, but called for a little bit more. So let me see what else. So the cost of that mix that you saw is 1.7% more than the reference. SCC, and here are some strength results. They tested the reference and the high filler at different times. They had some confusion there at the plant, but you can see the reference was 4,800 psi at 20 hours. Ours was 4,200 psi at 17.5, so it was not at the same time. So probably this is getting closer to the reference here, but at 7 days it went way higher, 32%. Okay. So, so this is an ongoing effort. So the next, there will be another testing, lab testing with them. We're going to refine in the lab before we go to the industrial trial. So in the end, we were able to obtain cut of 50% on type 1L, similar set time, similar early mechanical performance, similar cost. So we are scaling this up with this concrete producer. We have 2 more to go, so we have 3 total. This project is being funded until 2025. We're going to scale up with the 3 of them and we'll also address robustness. We want to see what changes in raw material variability, process variability, and other variabilities will affect the performance of high filler. We do bring the concrete rheometer at the plant because we want to estimate, we want to see what is the energy that the reference is taking out of their industrial mixer so we can try to match that. So again, we do account a lot, rely a lot on their experience to tell us if the concrete is good or bad, does it need to refine, and so on. So LCA is ongoing, and with that, I'm available for questions. Thank you.